Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, hello everyone. So it's my pleasure to introduce Asaf Schuster, who is visiting us. He's a professor at the Technion Institute in Israel, and he's been working for the last 15 years on distributed computing, data mining, parallelism, data streams, and he's hosted here in joint effort by the High Performance Computing Product Group and Microsoft Research, and where we're looking at the ways to program cluster machines better. Today he's going to talk about monitoring distributed data streams, and with that I'll give the word to Asaf.
Yeah. Thank you, Dan. Okay, so the talk today is about recent work that is joined with my student Tsachi Sharfman and Daniel Keren from the Haifa University. So in recent years, during the first years of this millennium, my group focused attention on processing of large databases. Basically, these are databases that are distributed among many machines, many disks. And the idea is to provide efficient processing of such distributed databases. We had many approaches that we came up with, and today I want to focus on the most recent of those, which we call the geometric approach. And this approach can actually handle distributed data streams. Was presented last year in SIGMOD, and there are several papers under different stages of writing and publication. So let's consider a first example as a web page frequency count. So suppose you have a distributed mirroring of web pages, and you want to keep track of the number of accesses to different pages, because if a different page is accessed a lot, then you want to add mirrors in different locations. And if a certain page is accessed not so much, then you want to remove those excessive mirrors that take resources. Okay, so suppose you have some. So let's consider monitoring a page, and this is going to be the green page. Okay, and we suppose we have some threshold for the frequency of accesses, and when this threshold is crossed, we want to get an alert, and so we add a mirror, or we remove a mirror, and so on. So first there are some accesses to the green page, but then there's some time when the green page is not accessed, so the threshold, so the amount of accesses reduces, crosses the threshold, and we remove some mirror. And then there are more accesses to the green page, and again we cross the threshold. And what we want to do, we want to be able to determine precisely when the threshold is crossed. Okay, so this is an example to a situation where you have a stream of data coming in at different places, distributed geographically, and you want to make sure that you pinpoint the exact point in time that a threshold is crossed for a certain function. In this example, the function of counting the rate of accesses to the green page. So what is the problem that we are talking about? More formally, there is a set of data sources. They are distributed. They produce new data items every now and then, periodically or occasionally. And a data vector, so a data item consists of several values, so we call it a data vector. So every local stream has a data vector, and the data vector is collected from the stream periodically, where the stream is infinite. So data items come every now and then. Data vectors are collected all the time. Or it can also be a large data set, the same methods that I'm going to describe for infinite streams are going to work for large data sets. Now, for an infinite stream, people usually try to focus on specific values, not always all the values that are collected from the streams. People talk about windows. These can be windows in time. So you say that the values that I'm now collecting from the stream is the average of the last 5 minutes, or the value, the data vectors that I'm now collecting from a certain stream is the average of the last 100 items that appeared on this stream, and so on and so forth. But this will not matter. It does not matter for us how you compute the windows. The problems that we are going to describe will remain, and the methods will remain the same. Okay, now we have a set of distributed data streams. We have all these data vectors that are collected. Now what do we want to do with them? We are given a function with a page, with the web pages. It was a counting function, but it can be any function over the average of the data vectors. And we are given a predetermined threshold. And we want to issue an alert precisely when the function crosses the threshold. Okay, so this is a kind of a continuous query. Okay, it's not a query that you issue to the database, it's computed, returns with an answer, and that is it. It's a query that stays there, and the database should issue an alert whenever the threshold is crossed. And what do we have as our goal? Our goal is to minimize the communication during the query execution. Okay, so there will be as a small number of messages needed to compute the answers to the query as possible. Let's see another example. So I've been here already for several weeks, and I can see that you guys are getting a kind of good air from the Pacific Ocean, but unfortunately, at the place where I live, in Haifa, there are refineries. And the refineries pollute the air quite intensively. And so what the mayor is doing, he's distributing sensors all over the city. And the sensors measure the concentration of various pollutants, carbon dioxide, sulfur dioxide, ozone, and so on. And then the concentration of pollutants determines some function which is called the air quality index. And when this air quality index, when this function crosses a certain threshold, the mayor calls the refineries and tells them to switch to a fuel which has less pollutants in it. Of course, it is more expensive, and of course, there's a question, why don't they always work with the less pollutants fuel? But this belongs to another talk. So the idea is that when the threshold is crossed from above, the refineries switch to a fuel which has more pollutants, and when the threshold is crossed from below, the refineries switch to a fuel having more pollutants, and so on and so forth. So this is yet another situation where you have many sensors distributed around the city, and only the average of all of the data vectors that is collected, this is a data vector of a concentration of pollutants from each of the sensors, the average of the data vectors that are collected from all the sensors that are distributed in the city determines the air quality index and determines the operation that is going to be taken. Let's switch to another example. The other example is a variance alert. So in this example, say you have a set of sensors inside a room, a conference room or machine room, and you want to make sure that the room is cooled evenly at every point, because if it's not, there will be some places that people or machines will suffer overheating, and some places that they will suffer overcooling, and there will be high energy consumption, so on and so forth. So these sensors actually monitor what is going on, and what they want to compute, the global function, is a variance over all sensors. When the variance crosses a certain threshold, there needs to be an alert that is issued and some tuning of the cooling of the air in the conference room. This is, by the way, the variance alert is actually a situation that appears in many cases. For instance, when you want to have even moisturing of fields when you grow crops. So you want to know that you water the field evenly. And this is very important for people who are growing stuff and want to make sure that the crops will come up evenly. Another example, you can consider a situation like you have currently in Google, or you will have, according to the CloudDB talk that I heard a few days ago with the live people. There are tens at the database that Google now maintains. There are tens of thousands of PCs, and this is, by the way, the same situation that will appear with CloudDB something like 2 or 3 years from now, as far as I heard from their presentation. They have tens of thousands of PCs. Each of these PCs is maintaining small fraction of a database. So the database is highly, widely distributed over a large number of disks and processing elements. And what you want to do, you want to issue information retrieval operation all the time on the global database. This basically usually takes a form of map-reduce operations, where the map is locally at each of the computing elements, extracts some data from the database, and then globally at the reduce stage, some global function is computed. For instance, you may want to compute the correlation index for all pairs of keywords in the database, which is higher than a certain threshold or a given bound. Okay, but there are a lot more information retrieval operations that people want to compute. They are all issued concurrently on the database, so communication becomes really a showstopper, because the bandwidth is not sufficient to support all the operations that you want to issue at the same time. And if you want to buy more expensive hardware, of course, this becomes the cost of the infrastructure, the communication infrastructure, sometimes dominates the cost of the whole thing. Okay, so this is yet another example. Finally, I want to focus on an example which will be my running example for this talk, which concerns distributed feature selection. Consider in this example, let's consider distributed mail servers that are distributed around the world, and they want to collaborate together in order to identify spam. Okay, so it's a distributed spam mail filtering system, and the system consists of a set of features that determine which mail is going to be considered as classified as spam, and which mail is going to be classified as not spam. And so we need to select a set of features, which may be words or concepts that are extracted from the mail, and these are used in order to build a spam classifier or a non-spam classifier, the same thing. Okay. And now a feature is, so this is, for instance, a stream of mail that you can consider it as a stream of mail coming in. This is mail 0, and there are 800,000 mails here that were received in this stream. And these are 3 features that appear in this stream: Bosnia, IPO, and February. And you can see how they behave, and they behave with respect to a certain function that we call information gain. And this function is going to determine to us whether the feature is a good classifier, is good to have in the set of feature set, or is not good to have in the set. So So the higher the information gain of a certain feature, the better it is for identifying spam or for identifying not spam. So, for instance, at the beginning of the stream, the feature February is not so good to identify spam or not spam, and then it becomes very good, and then its value is diminishing again, all depending on the data that is arriving during while the documents are flowing in with the stream. Okay, so basically what we want to do, we want to collaborate, the mail servers want to collaborate among themselves in order to compute the information gain, this function that I showed you of each and every feature, and to maintain the set of features that have the highest information gain. Okay, so what is this information gain? Yeah.
Since you're running example, there were some strange words like Bosnia.
Yes.
I didn't understand Nigeria. What is Bosnia doing?
I will get back to it after I show I'm now showing the problem. Then I'll show you the method. Then I'll show you the effect of the method on and then you'll understand what Bosnia is doing there. Okay, but for the time being, it's only a feature. It's like the same like It's the same like IPO and the February. It's an example feature. Okay, but what is important is that you want that you have in mind the picture of mail servers that reside on different continents and different states, and they want to collaborate together, and they get a stream of emails, and very intensive stream of emails, and want to collaborate on identifying the global value for this function, the information gain for all the features. So what is this information gain? Each of the mail servers has something that we call a contingency table. The contingency table is the amount of mail that was spam and in which the feature appeared, and the amount of mail that was spam and in which the feature did not appear. And the same for not spam, the amount of mail that was not spam and in which the feature appeared, and the amount of mail that was not spam and in which the feature did not appear. Of course, I assume here that the users of the system tag their mails as spam and not spam, and then we have feedback. But this is usually the case with the spam filters. They get feedback from how the client treats the emails that they tag. Anyway, so we have this contingency table, and this information gain function is defined on the contingency table. It's not so important. The function itself is not so important. It's the features, the characteristics of the functions are more important, and we'll see it immediately. Basically, what you can see is that when the feature will appear in all spam mail, this is going to be 0.5, and this is going to be 0.0, and the feature never appears in mail which is not spam. Then this is going to be the highest value 0.5, and this is going to be 0.0, and in this case, this feature is going to be a very good identifier for spam. It always appears when the mail is a spam, and it never appears when the mail is not spam. Similarly, when the feature will never appear when it's spam and will always appear when it's not spam, then this feature will be a very good classifier for not spam. Okay, so what we want the information gain to tell us is how close the matrix is for 0, 0, 0.5, 0.5, or vice versa, 0.5, 0.5, 0, 0, which will be the highest values for information gain. Okay, and the lowest will be when all the values on the contingency table will be more or less the same. So, for instance, when the feature is very good classifier for spam, in this situation, the information gain is maximal. It gets a value of 1. When the feature is very good classifier for not spam, the information gain is maximal. It gets a value of 1, which is a maximal value. However, on the average of those two contingency tables, the information gain is 0. Okay, because the average is equally distributed. Okay, so the feature is not a good classifier for anything. Okay, now this is a basic inherent problem that we are attacking in this work. Why is that so? Because you can see that in one of the mail servers, the feature can be a very good classifier. The information gain can be very high. The same in another mail server. But the global value in the system shows that the feature is no good. Okay, so there's no, and just to finish the sentence, so there's no local indications for the global, for what is happening globally. And this is a problem that we were attacking. Okay.
So what scenario would motivate a situation like that? Where within one mail server, you have some highly selective spam thing, and then, in another server you wouldn't?
Something that is geographically related. Okay, so the mail is specifically related to some geographical feature of what is happening. I don't know.
I guess I'm just sort of wondering, I know like in my mailbox, I pretty much get mail in all languages.
Okay.
So,
yeah, I agree that sometimes it will not be, sometimes it will be good to know what is happening in certain different areas. But I gave you, I thought I gave you so many examples of other situations that I now want to proceed with the understanding that mail that appears in one place will probably appear elsewhere very soon. But we need to determine globally what is happening. Yeah. Mm-hmm.
The coefficients in this matrix are the probability that it will be spam and it will have that. Right? So if you had 0.9 and 0.1,
this is still a very good classifier,
yeah.
But it's not the best. So, but it's not.
It just depends on how much of your mail is spam and how much is not spam. It doesn't have anything to do with the classifier.
Yeah, right.
So,
I agree. But you must. The reason that I put it this way is that the mail, the spam classifiers, they usually sample what the email to understand the amounts of features and the amount of spam and not spam and so on. So I was guessing that they sample in the same way, but later we'll return to your remark. Let's keep it in mind for a while. Okay, so again, the problem here is that you don't have local indication to what is happening globally. All right, and this was our initial point. So before I tell you what we did, let's survey some previous work. So previous work focused in general on aggregation functions. Aggregation function means that you count the number of things that are happening. You may average it out, you may sum it, but basically you count. And aggregation functions are relatively easy to do. You simply communicate only in order to know the current global value. You know where's the threshold. So you know the slackness between your current value and the threshold, and you simply split the slackness between the different streams. So each stream now has a certain spiel or slackness that is locally available. It can compute, it can go on receiving data inside this slackness, this local slackness, and when this local slackness is exhausted, then it is a local indication that something global may happen, and the global value can be recomputed, and so on. So basically, aggregation functions are relatively easy, and there were many works on aggregation functions. However, previous solutions for arbitrary functions, like the information gain and another function that I will show you soon, only naive algorithms were known. So the basic naive algorithm that was applied every time it was not an aggregation function was to move all the data to a central location and process it there. Meaning that in the examples that we are now discussing, all the mail should be moved to the same location, to a central location, and processed there. Which of course has a very high overhead in terms of communication, the bandwidth, the power, the amount of CPU cycles that are needed for the communication, the centralized resources that you need at the place where you process everything, all the data. And of course there are privacy issues. None of you wants his email to be moved to a central location just because a spam identifier is working there. Okay, so this was our beginning, and we took a different approach, as we call a geometric approach. What we did is we looked at the space of points on which the function is defined. We assume that the function is defined on a d-dimensional space. And we color this space so that the points on which the function is lower than the threshold is colored white, and the points where the function is higher than the threshold are colored in gray. And so here are three local places, three local streams, for instance, these red points. And this is a global average. And what you want to know whether the global average is white or it's gray. And more specifically, you want to be alerted precisely when this global average crosses this threshold surface. Let's see how it is in a movie. Okay, so you see that the local values of the streams progress as the streams keep coming in, and they move in white space, and the global average is over there. And at a certain point in time, the global average reaches the surface, the threshold surface, and precisely at this point we want to be alerted. But there's no local indication that this is happening, because at every local point, the local value of the function is white. It's below the threshold. And the global is already above the threshold. Okay. So the first observation that we had is that the global average is actually in the convex hull of all the local values. Okay? So if we have some way to monitor the convex hull of the local values and make sure that it is white, then we do not need to compute the global average. We know that it is white. Okay? So this was a first idea. It works as follows again. Okay, so you have a convex hull. It's drawn there. It makes progress, and you monitor the fact that it is all white, so you do not need to compute the global average itself, which is also drawn there as a plus. And what you want to do, you want to issue an alert precisely when the global average becomes gray. But with this system, with this idea, you'll issue an alert precisely now when the convex hull becomes non-monochromatic. So this is already a problem. Okay? Even if you have a way to monitor the monochromaticity of the convex hull, still the alert will come at the wrong place. And this is because the convex hull becomes very, very large. So we need a way to sometimes shrink the convex hull. What we can do is do the following. At certain points in time, we can compute the global average. Of course, the computation will require communication, but hopefully we will need to do it not so frequently. And once global average is known, then the convex hull actually shrinks to zero space. And now, when we start with zero space, the local values will start shifting away from the global average, from the last computed global average, with drift vectors. And now the observation is that the global statistics vector is always within the convex hull of the drift vectors. Let me show you this in a drawing. Okay, so at a certain point in time, we have empty diamonds, and the empty diamonds are the places where the local values were when the global average, which is a blue rectangle, was computed. Okay, and so everybody started with local values that were actually pointing there. And now each one of the local values, when the stream goes on, shifts from the place where it used to be, and this drift vector is also the drift vector from the previously computed global average. And now the observation says that the global of the current local points, which are the blue diamonds, is the same as the average of the drift vectors, which is always inside the convex hull of the drift vectors. So now we need to monitor the monochromaticity of a smaller convex hull. Okay? So that's, yeah.
So you assume that they synchronize on the global maximum, the blue square, and then from that compute the red dots.
Right.
But
from that, of course, each of them computes this difference, but this difference, when added to the global vector, is this drift vector.
Right. So the one on the lower right only knows the upper red dot, upper right red dot, but doesn't know
red
the other
dot? This one?
Yes, but
Yeah.
it doesn't know the other red dots.
It doesn't know. I assume all the time that I have some way to monitor the monochromaticity of the convex hull, of convex hulls in general. And all I wanted to do is to shrink the convex hull. Okay?
So you're going to show how to do the convex hull later?
In a moment. If you're already bored, I can jump there, but just in a second. Okay, so this is how it goes. Every time the convex hull becomes non-monochromatic, I recompute a global average. Okay, so here the convex hull becomes non-monochromatic. I immediately recompute a global average, and so on. This is already in the direction of an algorithm. All I need, yeah.
You seem to presume that it's easier to compute this monochromaticity of this little convex hull
Yeah.
than the average itself.
Exactly, yes.
Why that?
Why that? Okay, so this is an excellent question, because this is a slide that shows the crux of the whole thing. How am I going to monitor the monochromaticity of the convex hull only with local computing, with no global knowledge? So here's the theorem. The theorem was not known to computational geometry guys. Apparently was not known. At least Micha Sharir doesn't know it, and he's considered one of the gurus there. The theorem says as follows. Suppose you have a polygon in space, in d-dimensional space. Okay, here I show it in two-dimensional. In d-dimensional, it's a polygon with certain vertices, and fix any point inside the polygon, outside the polygon, does not matter. Here you see it inside the polygon. And now take the distance between this point and any vertex to be the diameter of a sphere. Okay, so here. The vertex takes this vector and draws a sphere whose diameter is the vector connecting it to this point. Okay? And now let all the vertices do the same. With this drawing, the theorem says that the convex hull is bounded by the union of spheres. Okay? Now, if this point, which is not the current point, is some previously computed point, is known to all the streams. So now suppose that the vertices are the local values of all the streams, and they have some agreed upon previously computed point, then each of them can compute its own sphere and the monochromaticity of its own sphere. And if all the spheres are monochromatic, we are assured that the convex hull is also monochromatic. Now, computing the monochromaticity of a single sphere is a local condition. So we already moved from a global condition to a local condition, and so the basic algorithm says as follows. You have an initial estimate vector, each of the streams maintains the monochromaticity of its sphere. Once any sphere becomes non-monochromatic, the stream, the local stream, triggers the global computation of a new estimate vector, and so on and so forth. And this goes as follows. So you can see that whenever the sphere becomes non-monochromatic, a new computation starts. Okay, and of course, we do not only monitor the convex hull, we monitor many points outside the convex hull. This is going to be a matter of optimization later, but at this point, what I showed you is that we could move from a global condition to local condition. This was our goal in life. Okay, so now we activated this algorithm on the Reuters corpus. The Reuters corpus consists of some 800,000 or more news stories that were collected between 1996 and 1997. And we consider this as a big stream of documents that is coming in. And the tagging of these stories did not contain spam and not spam, because at that time they did not have spam, but contains tagging for corporate industrial stories, which we consider to be a very good simulation of spam. And so we used that, and once again you can see the features that we are following. And now you can see that, for instance, Bosnia, at that point in time, in 1996, it was probably the end of the war, so it had a very high it was very high indication of non-corporate industrial story, the appearance of Bosnia inside the document. So this was a very good, it has very high information gain for identifying non-spam, okay, for non-corporate industrial stories. And at a certain point in time, it relaxed, but it stayed a fairly good identifier. If we follow February, then February starts as being in August. It starts as being not very good, not very high information gain, but then as time moves on, it becomes better and better until precisely in the month of February. February has a very good, a very high information gain, a relative information gain, and I don't know what exactly it identifies, corporate industrial or not corporate industrial stories. But it is a very good identifier for one of them. Okay, and then it drops again towards August, and probably it behaves like that all the time. And then if you follow IPO, IPO is always a good identifier for corporate industrial stories, so it vibrates around the information gain, the value of information gain 0.003. It remains stable the whole time, the whole year. Okay, and now if we look at the performance of the algorithm and we compare it to the naive algorithm, the naive algorithm would have to move all the stories to the same location, to a centralized location, and we compare it with the performance of our algorithm. So we see that at certain threshold, for instance, as a threshold 0.001, there's almost 5 orders of magnitude improvement in the amount of messages that we have to send, in the amount of documents that we have to send around. In very high threshold, again there is the same saving. However, if we move to the thresholds, middle thresholds, situation is not very good. It's not very bright, because, for instance, if we move to the threshold 0.003 for the feature IPO, the saving is less than 4-fold. And why is it the case? It is the case because if you think about it, then global average vectors will have to be computed all the time while the feature crosses from below and from above. Crosses vibrates below and above this threshold, so the saving here will not be that good. So in
this second graph here, you've got you're plotting the communication, the broadcast messages, right? But
the amount of documents.
You've got the naive algorithm is one series, and then your other 3 series are features. So I don't understand, what does that mean? Is this broadcast messages due to the features, or?
Forget about the fact that it's broadcast messages. Just think of it as we had several algorithms in the it's copied from the paper. Just think of it as all documents will have to be moved to a central location.
Right,
so basically, I just count all documents. And I think this is a 10-node situation. Okay, so I think each of the node would have 80,000 documents arriving at it with a stream. So this is why one of them was not moved. Okay, this is why it's not more than 800,000, but it's 750, something like that.
For each feature separately, right? So
this is computed for each feature separate. Yeah. I'll say something about it later. Okay, but now you understand the role of Bosnia in the whole thing, and you understand what we expect from the algorithm. Okay. Of course, it doesn't make sense to monitor thresholds that are crossed all the time. It doesn't make sense to monitor the threshold 0.003 for the feature IPO, right? But anyway, if this bothers you, then you can apply, then usually people apply as the following, an accuracy vs performance trade-off, and what they do, they set an error margin. So if this is the threshold surface, they just put another threshold surface just a little bit above it, and another threshold surface just below it. And so as long as you do not cross the virtual surface, which is in the gray area, then you don't bother recomputing the estimate vector. And the same when you come from the gray area and you advance towards the white area. You can see it here. If you count the number of computing of average estimate vector, you'll see that initially we have 7 of them. And then if we repeat the whole thing with error margins, we compute it only 4 times, which shows you that there's a substantial saving in having error margins. And the saving is better the more vibrations the feature does around this threshold. So you can see that for IPO, the saving is much better. And this is the drawing for 0.003 threshold, okay, than the others. But anyway, so error margin is one good optimization. And if you look at the scalability of the whole thing, you'll see that there is a fixed number of messages per node that we add to the system. We tested it only until 100. Believe it or not, we did not yet have time to test it for more nodes. It seems linear, but so it seems that for 100 nodes, you'll have the number of messages flowing in the system 4 times as the number of messages that you'll have with 25. But somehow it looks like there's some effect of becoming flat here, and we still need to look into it. Of course, this is the threshold 0.003, which is kind of high, and this is where the method is doing better than with the threshold 0.003, where the method is doing worse.
So if you have 100 nodes and only 5 of them cause the threshold to go over the
okay, very good question.
Would you?
Excellent question.
I mean, you know what the question is going to be.
Of course, and this is the answer. Okay, so you don't need. I'm just, I'm
going to ask another question after that.
Sure. As many as you wish. Anyway, here, what you can see, what was asked here is this is only one problematic stream that exists in the system. Okay, all other streams are well and they are very far away from the threshold. It's only one that is making all the trouble. What can we do with it? Should we recompute globally each time only because this one is moving, is doing a lot of movements with a value and creating large spheres that become non-monochromatic? So the answer is we do need to do some communication, but it does not need to be local. If this guy was able to find another one, for instance that guy, and to average out only with the other guy, creating this situation, this is their joint average, and their current sphere after averaging between themselves is this sphere, then we do not need global communication. We can have only point-to-point communication between them. Okay, so this is kind of an answer, and it's very, very, in the trials, in the experiments that we did, it appeared to be highly efficient.
But you want to keep a list of your mates. So the previous data point is that you have the global maximum or the global equilibrium.
Mm-hmm.
But to find your mate to compute the average with, some nodes may be better than others.
Exactly. But if you have a good method how to choose between those three, it will be I will be very happy. But it turned out that the situation is that if you have 100 and one of them behaves very badly, usually all the others are okay, and you simply need to choose randomly. But of course, this is a matter of further research and further optimization. Okay. Yeah.
So there is this objective convex hull.
Mm-hmm.
And so just to make sure I understand, so what you're discussing, how much bigger this sum of circles could be, or the area covered by circles, or
Mm-hmm.
volume covered by circles may be much bigger than the minimal convex hull that
I did not yet come to discuss it. I did not yet start with the optimizations on the amount of extra surface which does not need to be monitored but is still covered. Okay, I will get to it in a moment.
Isn't this part of the question which you discussed now?
I don't know, because I simply replace global communication with point-to-point communication here. The size of the spheres is still very large. Okay, but in a moment I'll mention something about it. So before I do that, I want to mention the computational complexity of calculating monochromaticity of spheres. The distance from the threshold surface, and it's not easy to compute in general. Okay, so for some functions, such as the variance, we have closed form solutions that are relatively efficient. For others, we will need to resort to numerical methods, and for others, we just issue offline computations at certain points and approximate the value. This is yet another direction of further research is needed, and there's a lot of literature about this. Regarding the performance analysis, a little bit more, rather than experiments, to do something more formal, let's look at two functions. This function and this periodic concentric circles and this function. Of course, the method would be a lot more efficient with this situation than on this. So the efficiency of the method basically depends also on the picture, on the way that the function on the function itself. But it is also dependent on two other parameters. The first parameter is the distance between the estimated global average and the threshold surface. Okay, because the the longer this distance is, the higher this distance is, the less chance that spheres that are created somewhere around here will become non-monochromatic. Okay? The second parameter is the variance of the local of the data that arrives at each stream locally. Okay, if one stream has a very high variance, then it will grow very large spheres, and we will need to communicate a lot. If the variance is relatively small, then there will not be a lot of communication. And of course, this is also shown in the bounds. You can see that the priority of violation and priority of communicating gets higher with the variance and gets smaller with the distance of the expected global average and the threshold surface. But is also getting smaller. The priority is also getting smaller as a function of the window size. Okay, so remember what I told you as the first slide. The window size is a number of elements that you average on at each stream before you hand in the data to the system. Okay, and why is the window size? Why does the window size has any effect of what is happening? Because, for instance, if you look at threshold 0.003 with IPO, which vibrates many times, when you enlarge the window size, it has an averaging effect. And an averaging effect will always say that the transitions, there will be a smaller number of transitions. Okay, so again, there's less impact on Bosnia and February than on IPO with this specific threshold. Regarding one of the things that was said here, until now we were only dealing with single features. Now, what about when you want to monitor all the features, because you want to maintain a set of the best features, so you need to monitor them all? What you can see here is that with the naive algorithm, you only move a single mail every time, or a single document every time. So you count only once. But with the many features, the more features that you have, it contributes a linear amount of communication. So eventually, when you have 4,000 features or a little bit more, you'll have the amount of communication equals the amount of the naive algorithm. So what can you do with that?
But that's a bandwidth. I mean, this measures round trips, not bandwidth.
Even if you multiply it by 2 or some constant factor, the same effect is shown here. Okay, so and this is the linear contribution of every new feature to the total amount of communication. It was Bazar's, is what Bazar's is here. Okay, so what can we do? If we look again at the problem with the contingency table, and for this example, just we choose another function, chi square, where chi square is very similar to information gain. You don't really need to look at the specifics of the function, but it digests a contingency table, and it is more or less saying the same as information gain, whether the feature is good or bad for classifying spam or not spam. Okay, and now I'm going to do a translation in my coordinate system. I'm going to move to a new coordinate system as follows. X4 is going to stay the same as before. So this is x1, x2, x3, x4. I'm going to move to y1, y2, y2, and y3, with x4 remaining the same. But what is important is that a translation for y1 is the amount of spam in the system. And it's independent of the specific feature that I am looking at. Okay, so it's the same for all the features. And now let's see what creates the most, all the amount of communication in the system. So if you look at it, this is how the features behave in the new coordinate system. And this is a manifold of chi square, which is a threshold surface. And you can see that some features move move below the surface and some move above the surface while I'm computing. But the movement that creates most of the difference between different times is the movement in the y1 axis, which is the amount of spam in the system. Okay, and when you come to think of it, when the amount of spam in the system grows high, it will create communication for everyone. For everybody, okay? All the features will have spheres that will become non-monochromatic, and all the features will start communicating. So what we can do, we can detect this, in this new coordinate system, we can detect for the specific coordinate y1, if this is the main contributor, then we compute it together for all the features and proceed from there. Okay, and it saves several, in situations of multi-feature, it saves a lot of communication. Okay, we also worked on tiered sensor networks. I just want to show you that in order to show you that for other data sets, the thing works as well. So in tiered sensor networks, the situation is that you have a tiered sensor network is composed of cells. In each of the cells, you have many sensors which are very simple and inexpensive and communicate only with a main sensor of the cell. This main sensor, which we call, what do we call it here, macro node, is more expensive and more stronger than the others, and this it can compute with other macro sensors that are close to its cell. Okay, so what you can do, you can activate the algorithm inside the cell, and then trigger a traditional distributed algorithm between the macro nodes. Okay. So I'm not going to go through the details here, but just to show you the effect on the data set. The data set is actually a real-life data set collected from from several thousand points on the northern hemisphere, where sensors were distributed by somebody, and the readings were taken every 6 hours in a period of year. Okay, so there's a very strong spatial and temporal correlation between the readings. And the average temperature, if you wonder about the weather, ranges between -3 point something to 15 degrees centigrade. Okay, this is on the northern hemisphere. And if you look at the results, so again, the naive algorithm should send all the data to a central location and process the data there. So what we wanted to do, we wanted to know whether the average temperature crosses a certain threshold. So here you have the threshold. This is actually the number of nodes for cheap sensors. Okay, so let's look at this picture. So again, with the naive algorithm, you'll have the whole system producing some close to a million messages, and with our algorithm, at certain threshold, for instance, -20 or 40 degrees centigrade, the amount of saving will be almost 6 orders of magnitude. Okay, and again, if you monitor thresholds or temperatures that are crossed very often, then the saving will be less evident. Yeah.
Quick question. It seems to me like the nature of this graph will depend a lot on your sampling rate, in some sense. So if you sample very frequently, then probably you don't cross your threshold very often, and you'll sort of look better relative to the naive algorithm. So in this particular scenario, like you're sampling like once per day, or something like that, or.
Yeah. I think you're referring to the window size, and of course, when the window size is larger, it has an averaging effect, and we already saw that it indeed saves communication.
Actually, it's not so much the window size so much as how much the window moves per you feel obligated to send every single data element that you get some central repository, then you're going to be sending a lot of data you don't really need to send, right? Whereas if every reading that you have is from a significantly different point in time, and you expect the variance from one point to the next in your window to be very large, then you would expect that the result of applying the average to the window would therefore vary significantly too, and would require more communication in the decent algorithm.
I agree. In other words, even when the global value shifts, you want it to shift smoothly. If it shifts like that, then you cross, at a certain point, you cross many times. Yeah. So an averaging effect, again, a larger window will have an averaging effect. And yeah. Okay, so there's also the other things that we saw here. Some words about shape sensitivity, which we mentioned before. You mentioned before. Again, when we look at the method, we see that the spheres cover a lot more points than actually needed in order to cover the basic convex hull. Okay, they cover points also outside the convex hull. So it would make sense, if we want to optimize the method, to try to make the spheres cover only those points on the convex hull. And if we cannot do this, try to adapt to the threshold surface. So there are three basic things that we can do. We can fit the cover to the data itself that comes in. We can fit the cover to the threshold surface. And we can have specific function classes which we know in advance this is going to be the function, so we optimize for this function. I want to show you only examples for the first two, what we can do. So suppose this is the data. Okay, this is the convex hull that we have in mind, that we have now, and this is, and we want to a cover which is optimized specifically to this convex hull. What can we do? So using a covariance matrix, we can rotate the thing to be parallel to the axis, and then we can inflate the axis to be more or less the same in every direction. And now we can compute spheres for each of the vertices. Okay, so this is the cover that we are going to get. And now we squash back the inflated thing into its squashed form, and we rotate it back. And as you can see, the best cover that we were able to find is composed of ellipsoids. And actually, with some non-trivial math, we can show that these are the best. If ellipsoids is what you use as your spheres, then with the covariance matrix you get the best covering ellipsoids that you can. And if you compare this to what we had before, to the spheres, to the round spheres, to the balls, you can see that the balls cover a lot more area outside the convex hull than what you get with ellipsoids. Okay, and I don't want to get into the details again. Another possibility is to fit. Yeah.
Which is that, to me, things like this sort of ask the question also. Right now you're considering techniques where each data point essentially needs to know about, one point that you're computing relative to all the others. Are there techniques that involve knowing about more than one point or something?
No.
Like that?
Wait. Okay, so again, what we have here is a situation that we want to locally compute a constraint that will tell you, that will give you an indication what is happening globally. But if you consider the monochromaticity of this ball, it covers many points outside the.
I understand. I guess I'm also asking another question, which is this is sort of, it sort of feels like this is what you can do with one more piece of information, global piece of information that you compute at one moment in time, relative to what you have. Suppose you let yourself compute two pieces of information rather than one.
Oh, I
Is
see.
there some obvious generalization of what you're doing here that
I'm sure there are. We did not do it yet. We did not think about it. I mean, there are several ways in which we are pursuing this work, and we did not yet think about the ones that you were raising here. Okay, so another optimization that we could think about is to fit the bounding region instead of trying to fit it to the data, fit it to the threshold surface itself. So here you have the threshold surface, and you have the estimated global vector here. And of course, if you have two local vectors, then they may be creating non-monochromatic spheres, unless you move the global point more into the center of the trusted area. Okay? If you knew that this would be the case, you would move the global point further into the center of the gray area. How can you do that? Look, the spheres are larger, but they are monochromatic this time. Okay? So how are we going to do that? We consider distance fields, which are equidistance places, geometric places from the threshold surface, and they are colored by the same color. Okay, so this place, for instance, which is colored in blue, has the same distance to the surface threshold, and all these places are colored in red. And in the middle, you can see there's a place, a geometric place, which is called the skeleton. If you move to the right or to the left, you get closer to the threshold surface. Okay, so intuitively, when you move the estimated global vector closer to the skeleton, you get better situations. The situation gets better. Okay, and indeed, we were able to prove some of it. We are still working on doing better. For instance, if you look with this threshold surface, and you have a global estimated vector, this is the global, this is a geometric space of all the places where if you draw a point and you have a vector connecting it to the estimated vector, and you put a sphere around this vector, it is still monochromatic. Okay, so this is a safe zone for this specific estimated vector with this specific threshold surface. So what can we do? We can now move the point to the center, to the skeleton, and see what happens to the safe zone. And indeed, the safe zone grows. Okay, so basically what we can show is that whenever you move the estimated vector closer to the skeleton, you get a larger safe zone. But it's not always the case, because look here. There are points where you move closer, and these points become outside the safe zone. So they will make, even though you move to a safer place, or intuitively to a safer place, you will create non-monochromatic spheres. Okay, so this is all what I wanted to say about the method. Now some conclusions. Regarding current and future work, there's a lot of future work regarding multi-feature situations, top K problems. There are many top K problems that we want to consider, and we still don't have good, clean solutions. Regarding the spherical bound, some things are still open there. I don't have time to get into this. The complexity of computing monochromaticity is also an issue of further research. Regarding large-scale networks, okay, whenever you need to compute a global estimate vector, whenever you assume that you can do it, then it means that you are not operating inside the large-scale network. You are operating in a relatively small network, not like the peer-to-peer network containing hundreds of thousands or millions of nodes. There you will never have the possibility to broadcast, and you will never have the possibility to agree on a certain global estimated vector. So we need to search for some local models that will generalize this, and we were able to do it previously with previous publication for other methods that we had. Computations that are non-threshold. We have some generalizations there. We are working on them for generalized computations. And stream fusion, when not all the data vectors arriving from different directions are the same, they contain different elements of the data vector. But still, you want to fuse everyone to the same system. And there are many other directions here for further research. And I would like to make one last remark on what this method is useful for. Okay, so until now I was talking about distributed systems. Okay, so mail servers that are distributed on many places, sensors that are distributed, and so on. Okay, or thousands or clusters containing a lot of a distributed database. But what if we only have a poor one single multi-core machine with 10 or 20 cores? And we want to use a multi-core machine because we have a lot of data coming in, and we want to process it fast. So each of the cores is actually working locally very, very hard. Do we really need, but we have a very fast communication between the cores. Do we actually need method like what I now described? Or is it only for distributed systems? So is there a scalability issue for multi-core systems? And my answer, my personal answer, is that with a lot of data, like the systems that you target with the P-Link, for instance, with the P-Link system, you do have a scalability issue. And the reason is that if you need to move all the data to the same core to decide on some function, why do you need parallelism at all? Okay, so there are functions that for computing them, you will need such methods, such techniques, even if you work on a very fast communication platform, such as a multi-core system. And indeed, we were approached by IBM. They recently bought a startup that was doing security of the network, and what they were doing, they were processing a lot of packets that were coming in. Okay, so they were working with symmetric multiprocessors of several cores, processing huge chunks of packets that come in on the fly in real time, and they want to know in real time whether there is a security threat. So each of the cores would work on his chunk of packets that come in, but they do need to maintain some global state of the security function itself that they compute. And this global state creates a lot of congestion between the cores. They communicate between themselves so much that it clogs the whole thing. Okay, and this becomes a barrier for the operation of the whole system. So they are now considering using this in order to resolve the problem. Yeah.
So it sounds like what you're saying is that in that particular problem, though, they were able to hold. They're basically able to hold all of the data inside the CPU. They didn't really have to, the main memory bottleneck wasn't significant. It sounds like you're saying, because all the cores share the same bus to main memory, right?
Yeah, all the cores share the same bus, but so the bus is busy in bringing a lot of packets and distributing it between the cores. Now, if the cores still need to somehow share between themselves intensively lots of data or lots of partial computations, this would jeopardize the operation of the whole thing. Okay? So I guess we had some questions in real time, but this is the time for more.
So I understand the idea is that locally compute as much as possible, even if whatever little computation needs to be done centrally is very expensive. So suppose we go to the limit. Doesn't matter how we pay for central computation. It's just we want to minimize the communication complexity, number of messages. So is there a kind of informational and lower bound? How do you know how close you are to the possible kind of objective limit?
That's a very good question. With this method, I know. Because I know every time that I cross a threshold, I will need at least one alert to be issued. Okay. So I have some. There's still some slackness. There's still some way to go from this method until I reach the very low, the lower bound that you have in mind. But if you consider the lower bound of this specific method, okay, because you need to synchronize everyone every time there is a, then we are fairly close. We are about factor 4 or 5 from the. I mean, this I call this fairly close, but we are about factor 15 or 17, sometimes 20, up to 25. From the very bottom lower bound that I can prove that any method will bump into.
Is this basically the error associated with triggering things because of the sort of the white area, you know, outside the sphere, you know, containing the threshold crossover point, even though the context will.
Of course, yes, and I mean, ideally, if you don't cross a threshold, you never need to say anything, but we will have to say we will have to at least initialize the nodes. And now, if you cross it once, how many messages do you need to do? So this is a kind of lower bound that we have in mind. We don't have. We are looking for some kind of lower bound that will say, okay, no method will reach the ultimate lower bound of sending no message if the threshold is not crossed. But perhaps there is a method that will do better than our technique. Okay? So we are looking for a lower bound that says every method will need at least some with some non-trivial considerations, and we don't have it. Thank you very much.
Thanks.